questions 8 through 10 on the 2011 grade 12 Euclid math contest. The Seath of Sundaram uses the following infinite table of positive integers. The numbers in each row in the table form an arithmetic sequence. The numbers in each column in the table form an arithmetic sequence. The first 4 entries in each of the 4 first rows and columns are shown. Determine the number in the 50th row and 40th column. Well, let's discuss this. Let's write out what they have given us, and then we'll add a few more rows. Now, if you look at it from a horizontal perspective, the first row, 4, 7, 10, and 13, obviously the first term is 4, that's my A, but my D, my difference, is 3. And the reason I'm using A and D is because arithmetic sequences are of the form A plus D, A plus 2D, A plus 3D, and so on. Now let's look at the second one. My A here is 7. My D this time is 5. In the third row, it's 10 and 7. And in the fourth row, it's 13 and 9, I believe. Yeah. So let's just write a few more. Well, I don't think we need too many. I just want to illustrate a few things. The next one, but how do we get the next row? I completely understand how to get the next number. You just keep adding D, whatever value the D is. But how do I get the next row? Well, keep in mind that these are also arithmetic sequences. They even tell you that in the question. So it's 4, 7, 9, 10, 13, 16, 19, like that. Where D in this case is also 3. In the same kind of way, that's also an arithmetic sequence. 7, 12, 17, 22. D in that one is 5. So this is going to be 27, and this is 32. And similarly, this one, the D is 7. So this is going to be 38, 45. And this one, the next column, the D is 9, so 49, 58, like that. I just wanted to do a few more just to kind of give an idea of what this looks like. Now, let's start looking at the rows. This is, of course, the first row, row number 1. This is row number 2, row number 3, row number 4, row number 5, row number 6. And then they are talking about the 50th row. So 50. I have to figure out the 50th row. Now, the first thing I can do is figure out what is the first term in that 50th row, this term right here. And I can do that by looking at this column. That column is an arithmetic sequence, and every term in that column is of the form 4 plus n minus 1 times d, right? 4 is the first term, and then n minus 1 times d, where d is the difference. But we know that d is 3. So this is really just 4 plus n minus 1 times 3, where n is the row number. Now, if I want the 50th row, I would put 50 for n. So it would be 50 minus 1 times 3, and that is 49 times 3 plus 4, which is 151. So the 151 goes right here. It's the first term in the 50th row, or the 50th term in the first column, whichever way you want to say it. So that is our starting point for that row. Now, I want the 40th column. This was the first column. They want the 40th column. Okay, to get the 40th column, I obviously need to know the D for this row. Well, let's go back to our A's and D's here. This is 16, and the D in this case is 11. And this is 19, and the D in this row is 13. As you can see, the D's are going up by 2 every time. I think that's a pretty clear pattern. So that means the D, in general, is going to be 3 plus r minus 1 times 2. That's something I'm getting directly from those numbers, where r is the row number. So for example, when r was 6, the difference was 3 plus 6 minus 1, which is 5, times 2. And that is 13. And that's why this is a 13. So I want the d that's going to go here. The d that corresponds to the 50th row. Well, I would put 50 for r. So d would be equal to 3 plus 50 minus 1 times 2. And therefore d is 50 minus 1, 49 times 2, 98. 98 plus 3 is 101. So that's my 101 right there. That is the difference for this row. And the a for that row, which is the first term, well, that's just 151. All right, so far so good. Now I am interested in the 40th column of this row. Well, every term in that row is of the following form: 151 plus the column number minus 1 times the difference, and the difference is d. Now, we know these numbers. The column that we are interested in is the 40th column, so that's going to be 40. And the d we calculated earlier as 101. So I'll put the 101 there. And then you just have to do this math here. 151 times 39 times 101. And that is 4090. This is the number that is in the 50th row and 40th column. Determine a formula for the number in the Arth row and Seath column. Okay. Well, the good news is that we have already done a lot of that math here. So I can just use a lot of what I've already found out to figure out that general formula. Well, how did we figure out this number 4090 previously? Well, we had to initially start off with the first term. Well, the first term we got over here, and that was with this formula. It was basically 4 plus n minus 1d, and n represented the row number. So they're calling the row number r, so I'll just call it r instead of n. r minus 1 times d. That is how I figure out that first number. But d was 3 for that very first column. So I put 3 there. Then that is how I got this 151. Then, of course, I have to add this c minus 1 plus d. C minus 1, which c represents the column, and this d. But this d is right here. That's the formula for d. So I'll put that in there. 3 plus r minus 1 times 2. And that's it. This is the general formula. I'm assuming they want you to simplify it a little bit. Okay, let's simplify this as much as we can. So this will be 4 plus 3r minus 3 plus c minus 1 times, this is going to be 2r, and then 3 minus 2, so that's going to be plus 1. And then this becomes 3r plus 1. If you expand this, it'll become 2cr plus c minus 2r minus 1. And let's see here, these minus 1 minus 1 cancel. The 3r and 2r just become r. So I have r plus c plus 2cr. I think that's about as far as it goes in terms of simplification. So this is the general formula. Prove that if n is an entry in the table, then 2n plus 1 is composite. A composite number is basically any number that's not a prime. So for example, 9 is a composite number because it can be divided by some number. Like for example, 9 is divisible by 3. But 7 is not a composite number, it's a prime. 7 cannot be divided by any number other than 1 and itself. So that's just a very quick refreshment of your memory to remember what is composite. Now we have to prove that 2n plus 1 is composite. Well, what is n first of all? N is any entry in the table, and any entry in the table is represented by that formula that we got in the previous part of the question. So now we have to calculate first of all 2n plus 1, and then our strategy is to show that it's not a prime, meaning it can be the product of two different numbers that are not 1. So for example, 11 is a prime number, right? It cannot be broken down into two numbers. I mean, the only possibilities are 11 and 1. But other than that, it can't. But if you have something like 12, that can definitely be broken down into two numbers other than 1 and itself, 2 times 6. So if we can show that 2n plus 1 can be broken down into two numbers that are both greater than 1, that will prove that it's composite. So here we go. First of all, we have to figure out what is 2n plus 1. So that's going to be 2 times r plus c plus 2cr plus 1. Expanding, we get 2r plus 2c plus 4cr plus 1. And now we have to do a little bit of factoring. I think if I factor out the 2r, I will be able to get 1 from here and a 2c from there. And I'm left with just 2c plus 1. All right, well, 2c plus 1 I can factor. From here, I'll just get a 2r. And from here, I'll get 1. So there we go. 2n plus 1 is factored into two numbers. Now, each of these numbers we have to show is greater than 1, and it is, right? Because c is a number, it represents the number of columns. R is a number, it represents the number of rows. So immediately, you're multiplying both of them by 2. So immediately, even if it was 1, when you multiply it by 2, it's 2. And then on top of that, you're adding 1. So they're definitely going to be bigger than 1. This number and this number will definitely be both greater than 1. So, since 2n plus 1 is the product of two integers, and both of those integers are greater than 1, 2n plus 1 is composite. And that completes our proof. Let x bracket denote the greatest integer less than or equal to x. For example, 3.1 bracket is 3, and negative 1.4 bracket is negative 2. Suppose that f at n is equal to 2n minus 1 plus the square root of 8n minus 7 all over 2 bracket, and g at n is 2n plus 1 plus 8n minus 7 square root over 2 bracket for each positive integer n. Determine the value of g to the 2001. G to the 2001 is a direct substitution into that equation right there. So it would be 2 times 2001, because n is 2001, plus 1 plus 8 times 2001 minus 7 under the square root sign, all over 2, and this bracket. Okay, let's figure this out. This will be 4022. And this is going to be 1 plus, if you do that math there, it's 16081 under the square root sign, all over 2, surrounded by this bracket. This is 4022. And this becomes approximately 63.905. And then that symbol basically means that you get the greatest integer less than or equal to that number, which is 63. And then if you add those two numbers, you get 4085. So that is the answer to part A. Part B, determine a value of n for which f at n is equal to 100. F at n we want equal to 100. And 100, therefore, will be equal to 2n minus this expression 1 plus 8n minus 7 all over 2, like that. Okay, well, obviously I have to drop that bracket in order to get some solution, and then at the end we'll use trial and error to see what integer value of n actually works. So this just becomes 100 is equal to 2n minus that. Multiply through by 2 to get rid of the fraction. And bring that over to the other side. You get 1 plus 8n minus 7. And then bring that over 4n minus 200. And if you just isolate for the radical, you'll get 4n. You're subtracting 1 from each side, so it's minus 201, like that. And now we can square both sides, and you get 8n minus 7. And that squared, if you expand it out, it'll be 16n squared minus 2 actually, times 4 times 201, and then plus 201 squared. And then now we can collect like terms, put everything on one side, and if we do, we get 16n squared. This big number, subtract from it minus 8n, and you will get minus 1616n, and then the very last number at the end is a big one. It's 40408, and you can divide through by 16, and we'll just be left with n squared minus 101n plus 2525.5. Now we'll use a quadratic, since that's pretty difficult to factor. So n will be minus b, so plus or minus the square root of b squared minus 4ac, 2525.5, all over 2a. So this becomes 101 plus or minus 10201 minus 10102 all over 2, and that gives me 101 plus or minus 99 all over 2. So we got two solutions. We got the first one, which is 55.47 approximately, and then 45.52. So these are obviously not integers, because n has to be an integer. So what I'll do is I'll use n equals 55, n equals 56, 45, and 46. I'll use those four values and see which of those satisfies that, makes it f at n equal to 100. So I'll let you do that, because it's pretty straightforward. You just have to substitute n into this. But I'll do it here for the one that actually works, because only one of those actually works, by the way. And the one that works is f at n being f at 55, when n is 55. You just substitute it into this formula right there. So you get 2 times 55 minus 1 plus 8 times 55 minus 7, all under the square root, all over 2. And don't forget that bracket. This is going to be 110. And this whole thing, when you do that math, it becomes 10.9 under the bracket. And that's going to be 110 minus 10. And that, of course, is 100. So this works for n equals 55. Suppose that A is equal to f at 1, f at 2, f at 3, and so on, and B is equal to g at 1, g at 2, g at 3, and so on. That is, A is the range of f, and B is the range of g. Prove that every positive integer m is an element of exactly one of A or B. You'll notice that both f at n and g at n have this term that's common. That is the same for both. One's a minus and one's a plus. So we need to analyze that term. And let's just let it equal k. So that means that this term is going to be equal to k, but it's going to be less than k plus 1. That's what that definition means. And we are looking really at what is inside those brackets. So like this. Now we will need to isolate this inequality just for n, and I'll take you through all the steps for doing that. So first multiply through by 2, then subtract 1 from both sides. Now square both sides to get rid of that radical, and then add 7 to both sides. And finally, to isolate for n, divide through by 8. So now we have isolated for n, and we can do a little bit of factoring here to make it look a little bit better, like that. And now this term right here is kind of similar to that term. So I'm going to try to make something equal to it. I'll just call tk equal to that term right there, 1/2 k times k plus 1. And therefore, if we have tk minus 1, it becomes 1/2 k minus 1 times k minus 1 plus 1, which is k. So this expression really just becomes, with my substitutions, tk minus 1 plus 1 is less than or equal to n, which is less than tk plus 1. And that is equivalent to tk minus 1 plus 1 less than or equal to tk. And we can also write tk plus 1 is less than or equal to n, which is less than or equal to tk plus 1, like that. That's completely fine. Now we're going to look at both of these one at a time. First we'll look at f at n, and then we'll look at g at n. Or g at n first and f at n. It doesn't really matter, but let's start with the first one. So let's start with this one first. I've got tk minus 1 plus 1 is less than n, and that's less than or equal to tk. And tk minus 1, if we multiply through by 2, we are going to get the following: 2tk minus 1 plus 2, 2n, and this is 2tk. Now tk minus 1 is this, and tk is this, so we can put in those values. But first, let's get this middle term to look like g at n, because that is my goal. Well, in order to do that, I have to add k to it, 2n plus k, like that. And that's going to mean that this also is going to have k added, and so will this on this side, plus 2 plus k. Now at this point, this is g at n. If you recall, g at n was 2n plus this, and this is my k. See, right here. So that's why this is g at n. So I have g at n is less than or equal to those two. Now I can put in my values for tk and tk minus 1. Well, tk is right here. So 2tk would just be k times k plus 1. and then I've got this plus k. And then 2 times tk minus 1, well, tk minus 1 is right here, so if I multiply it by 2, it's just k minus 1 times k. And then don't forget the plus 2 plus k. Now let's expand this, and when you do, you get k squared minus k plus 2 plus k less than or equal to g at n, and less than or equal to, let's expand this, k squared plus k plus k. On this side, all we get left with is just k squared plus 2 less than or equal to g at n less than or equal to k squared plus 2k. So that means g at n, all of g at n, are values as follows: k squared plus 2, k squared plus 4, k squared plus 6, dot, 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 all the way to the last one, which is going to be k squared plus 2k, like this. And the 2k's, whatever k is, if k, for example, was 5, it would be 2, 4, 6, 8, all the way up until 10. So as you can see, it's k squared adding multiples of 2. So now we're going to do the exact same thing with this one right here, the next one. And this will help us figure out the same kind of inequality for f at n. So we have now starting point is going to be tk plus 1 less than or equal to n, which is less than or equal to tk plus 1. And the only difference here is that because we're going up 1 before we had tk and now we have k plus 1, our value that we have right here, instead of k, will be k plus 1. So we're going to substitute for this, instead of k, we're going to substitute that being equivalent to k plus 1. So now here we go. Again, just like before, let's multiply through by 2. Now we have to subtract this in order to get f at n, because if you recall, f at n was 2n minus this term right here. So we have to subtract it this time. So it would be 2n minus 1 plus the square root of 8n minus 7 over 2 under the brackets. And then remember, because it's k plus 1 this time, this is equivalent to k plus 1. So since we subtracted this term, we have to subtract k plus 1 from both sides. So this becomes 2k plus 2 minus k plus 1. And similarly on the other side, it's tk plus 1 minus k plus 1. And as before, tk is this right here. So if you multiply it by 2, it just becomes k times k plus 1. And we have plus 2 minus k minus 1. This whole term is really just f at n. So put that in there. And then tk plus 1 is going to be, if you use these standard definitions, k plus 1 times k plus 2. So if you multiply through by 2, it will be k plus 1 times k plus 2. And then, of course, we've got to subtract that k minus 1 like that, taking it out of the brackets. Now let's do some simplifying here. We're going to have k squared plus k. So we're going to have k squared plus k minus k. So the k's cancel. And then you're just going to have 2 right there, like that. But the 2, you have to subtract the 1. So you're really just going to have 1. And then that's less than or equal to f at n. And then this one, if you expand it and collect like terms, you'll get k squared plus 3k plus 2. But then you have to subtract minus k minus 1. So that's just going to leave you with k squared plus 2k plus 1. And this range will basically be values as follows. It will be values like k squared plus 1, k squared plus 3, k squared plus 5, dot, 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 all the way until you get to k squared plus 2k plus 1. So this time, as you can see, you're adding odd numbers every time to k squared. So our conclusion, therefore, is that both of these ranges, this is the first range and this is the second range. This is the range, of course, for g at n, and this is the range for f at n. Both of those ranges contain all the integers that you could possibly have, all positive integers, and none of those will overlap. And that is pretty much what they wanted us to show. In the diagram, 2 times the angle BAC is equal to 3 times the angle of ABC, and K lies on BC such that angle KAC is equal to 2 times angle KAB. Suppose that BC is equal to A, AC is equal to B, AB is C, AK is D, and BK is X. Prove that D is equal to BC over A, and X is equal to A squared minus B squared over A. First, let's look at this diagram. Let's talk about this. First, they tell us that those two angles have that relationship. So that basically means if 2BAC is equal to 3 times ABC, that means this is 2 theta, and BAC, this whole angle, is 3 theta. So that's our first relationship. The next one is this one, KAC is equal to 2KAB. So if KAC is equal to 2 theta, or let's use a different one, let's use alpha, 2 alpha, then that means that KAB is alpha. So that means if you add 2 plus 1, that's 3. So 3 alpha is the same as 3 theta. So that means alpha is equal to theta. And that's a very important point. Now let's tackle this proof that we have to do. Well, let's look at it from the perspective of the triangle rule with regard to areas. If you have a triangle, let's say like this, and we have 2 sides given to us, say A and B, and we have an angle there, the area is equal to 1/2 times the side A times B times the sine of that angle C, so this angle right here. So we're going to use the same to figure out this whole thing right here, the same formula. So the total area of that entire triangle ABC is equal to the area of the 2 smaller triangles, this first one, AKB and AKC. So we can call it area 1 plus area 2. Or if you want to use letters, like that. So total area, we can use any of these sides. Let's label them first. So this is going to be 1/2 AC, and I'm going to use that sine 2 theta right there, this one. And then AKB, I'm going to use the same formula, CX, again times the sine of 2 theta. And then AKC is going to be 1/2 B, and I'll use this side is D from A to K. So it's going to be 1/2 BD, and again the sine of 2 alpha, but it's really 2 theta because alpha is equal to theta. We got that up there. Now a lot of this cancels, the halves cancel, the sine 2 thetas all disappear, so all you're left with is just AC is equal to CX plus BD, like that. Now at this point, we're trying to make it look like this, right? So let's see what we can do here. We can subtract AC minus CX is equal to BD. We can at this point factor out a C, and then get A minus X is equal to B times D. And then I can bring the B into the denominator. So A minus X over B, like this. Now at this point, this is as far as I can go with this relationship, but I can find something else that will help. Now we will use the sine law. And the sine law is very helpful, and we'll use it on two triangles. We'll use it on this one, ACK, and then we'll use it on the other triangle, ABC. And before we do, we can do a little bit of fancy values, looking at the values of the angles. If this is theta, right, theta is equal to alpha, and this is 2 theta, then this is obviously, this angle in here is 180 minus 3 theta. And therefore this angle is 3 theta, because those two angles have to add up to 180. So here we go. With ACK, that is going to give me the sine of 3 theta over B is equal to the sine of 2 alpha, or 2 theta, over A. So if you simplify this, you can get that, actually it's not A, it's A minus X, because I'm looking at this just this part right here, because that's the part that's opposite of 2 alpha, which is 2 theta. So now we can simplify, and when we do, we get sine 2 theta over sine 3 theta is the same as A minus X over B. So I just cross multiplied a little bit. Now let's look at triangle ABC. On that one, sine 2 theta over B is the same as the sine of 3 theta over A. And similarly, if I put sine 2 theta over sine of 3 theta, I get B over A. So now I have two relationships for the sine of 2 theta over the sine of 3 theta, so I can set them equal to each other. That means that A minus X over B is the same as B over A. So that means that A minus X times A is the same as B squared. Now A minus X over B is B over A, so I can make that substitution, B over A. And guess what? That proves the first one. Prove that D is equal to BC over A. I just proved it. D is indeed equal to BC over A. So that's done. Now with this one, I think I can prove the second one. Let's see, we already cross multiply. Let's expand this now. So we got A squared minus AX is equal to B squared. And then A squared minus B squared, put the AX on the other side. And then divide through by A. And you get A squared minus B squared over A. And there we go. We just proved the second one. This one right here. Prove that A squared minus B squared times A squared minus B squared plus AC is equal to B squared times C squared. Well, we can use our findings in the previous one. We have already proven this and that, so we can use those to help us with the next part. So we are trying to prove this, A squared minus B squared times A squared minus B squared plus AC is equal to B squared times C squared, like this. Well, we know that A squared minus B squared from that equation is equal to XA, if you were to rearrange that one. And then this one just becomes XA, like that. right? Because if you look at this equation, you've multiplied through by a, you get xa is equal to a squared minus b squared. So that's why I can make that substitution. And then this is just AC. And then this one right here is similar to that one. In that one, if you remember, it just says D is equal to BC over A. If we cross multiply, you get AD is equal to BC. And if you square both sides to make it look like that, it becomes A squared D squared is equal to B squared C squared. So I can substitute A squared D squared like this. So now let's do a little bit of factoring here. If I factor out the A from this guy, I get an A, and then in the brackets I just get x plus c, and that's equal to a squared d squared. Well, this is a squared and this is a squared, so those cancel. So all I am left with is just x times x plus c is equal to d squared. If I can prove that, I have pretty much proven this. So I will concentrate on trying to prove this right here, because that is the equivalent, and we have already proven these two. So let's go. Let's proceed with this question. I'm going to first use the cosine law on triangle AKB. So AKB is right here in viewing distance, and I labeled it according to what the original question had told me. So using the cosine law on that triangle, we have d squared is equal to x squared plus c squared minus 2xc cos 2 theta. And we have a cos 2 theta, so I'd like to make that into a just theta. And that double angle identity, basically, I'll put 2 cos squared theta minus 1. That's one of those double angle identities. And I think that's about as far as I can go there. Now, let's turn our attention again to the same triangle, AKB, but this time let's use the sine law. And that will help me, I think, with some substitutions. Sine law this time on triangle AKB. And we get the following. We get x over the sine of theta is the same as d over the sine of 2 theta. Now, again, I don't want to have double angles in there, so I'm going to put the double angle identity. Sine 2 theta is 2 sine theta cos theta, like this. Well, the good news is sine thetas cancel, so all I am left with is just x. I can actually make it look similar to what we have on the other side. So let me isolate for cos theta. X cos theta times 2 is going to be just d. So that means 2 cos theta is d over x. Okay. So that means cos theta is really just the same as d over 2x. All right, so now I can start substituting. This cos theta squared, I will substitute d over 2x for cos theta. So I've got d squared plus, equals x squared plus c squared minus 2xc. And then I've got 2 times cos theta squared. Well, cos theta is d over 2x, so that's going to become d squared over 4x squared minus 1, like that. Now let's keep going here. This is x squared plus c squared. That doesn't change, but when I multiply this out, I'm going to have minus 4 d squared c over 4x. And you're going to have a plus 2xc, like that. And this is, of course, d squared. So let's bring that over on the other side. D squared plus 4d squared c over 4x, like this. And, of course, the 4's cancel. So we don't need those 4's. Top and bottom, those will cancel. And on this side, we will have just x squared plus 2xc plus c squared. This side can be factored perfectly, x plus c squared, like that. And this side is, I guess if I want to add the fraction, multiply top and bottom by x, I'll get x d squared plus d squared c over x, like this. And then cross multiply and bring this x over, so x plus c, like that. And then on this side, factor out a d squared and you get x plus c. And then looks like the x plus c's can cancel from both sides, at least one of them can. So you're just left with d squared is equal to x times x plus c. And there you go. We just proved that d squared is equal to x times x plus c, and that's exactly what we had to prove in order to prove this whole question. So with the cosine law and the sine law, we were able to do it. So we have just proven that this is indeed equal to that. Determine a triangle with positive integer side lengths a, b, c and positive area that satisfies the condition in part B. So we are asked to find ABC such that a squared minus b squared times a squared minus b squared plus ac is equal to b squared times c squared. And keep in mind that because a, b, c are forming the sides of a triangle, we always have to understand that the triangle inequality also has to hold true. So if you have any triangle with sides ABC, the triangle inequality states that a plus b is greater than c. All right, so here we go. The first thing we have to do is simplify this a little bit to make it look like a quadratic equation where my x is actually going to be c. And let's proceed by doing the following. You can expand it out like that. And now let's put everything on one side and let it equal 0. And now we've got pretty much a quadratic equation. And of course, these are our coefficients right here. So it's a little bit strange, but the quadratic formula will be sufficient. So as always, minus b, in this case it'll be a times a squared minus b squared, plus or minus the square root of b squared. So that's going to be a squared times a squared minus b squared, all squared, plus 4a, which in this case is b squared, and times c. It's minus 4ac, but the minus and this minus cancel each other out. So you just get a squared minus b squared, all squared, all over 2 times a, which in this case is b squared. So let's try to simplify what's under the radical sign. If you factor out the a squared minus b squared, all squared, on the other side, other factor will just be a squared plus 4b squared, like that. And that's all under the square root sign. And that's all over 2b squared, like this. And the good news is that when you take the square root of that, it just becomes a squared minus b squared. And this part, unfortunately, is still under the square root sign. A squared plus b squared. A squared plus 4b squared. And of course, all of that is over 2b squared. Now, let's pause for a minute. Let's talk about this. This has to be an integer. But even if it's not an integer, it has to be at least a real number. And the only way it's going to be a real number is if this is an integer. So this is where the trial and error part of the question comes in, and we have to start plugging in values to try to make this an integer. a squared plus 4b squared. And after some trial and error, you get, if a is 16 and b is 15, it will become an integer. A squared plus 4b squared under the square root sign becomes 16 squared plus 4 times 15 squared under the square root sign, and that is 256 plus 225 times 4, which is 900 under the square root sign, and that is 1156, and the square root of that is 34. So that's how you get an integer. All right, let's figure out c then. 16, and this is 16 squared, 256 minus 225, plus or minus. Well, let's just use the plus because we want a positive number because the numbers represent the side of a triangle. So I'll use the positive one. 256 minus 225. And then I've got this, which I already calculated to be 34. And don't forget that it's all over 2b squared. So 2 times 15 squared, which is 225. So this is 16 times 31 plus 31 times 34. And that's all over 450. And that is 496 plus 1054 over 450. And that is equal to 1550 over 450. Divide top and bottom by 50, and you get 31 over 9. So there we go. I've got myself a triple. A, B, C. A is equal to 16, 15, and 31 over 9. The only problem is that A, B, and C must be integers. That was one of the criteria. So no problem. What we can do is just scale it up by multiplying by a factor. And that's perfectly allowed, since if you did that, the original equation would still hold true. That equation, of course, being right here. It would still hold true if you multiply by a factor. So the easiest way to get this into integers is to multiply through by 9. And when you do, you get values of 144, 135, and of course 31. And these three, 144, 135, and 31, will satisfy this equation right here. And also, those three numbers satisfy the triangle inequality that two sides are greater than the third side. So this is a possible solution for this question.